So last time we looked at low mass stars. Now we're going to start looking at high mass stars. High mass stars are the ones that have over 3 solar masses, over 3 times the mass of our Sun. Now before we get too much into the differences in their life cycle, something I want to point out is actually their formation. So all stars form in the same way and in the same place. However, something I want to show you, here we have a simulated star cluster. Okay, specifically we're looking at the HR diagram. So notice we've got temperature along the bottom with hot on the left and cool on the right, and up and down we've got luminosity. So this is just the HR diagram as we've seen before. So we have all of the stars start over here in the top right, where we expect protostars to first appear on the main sequence. Also notice that we have relatively few high mass and lots of low mass, exactly what we would expect. Well, as the simulation goes, notice that the high mass stars are the ones to reach over to the main sequence first. And then over time, the lower mass start reaching the main sequence, and about the time that the lowest mass stars are finally on the main sequence, the highest mass stars have actually begun to die out. What this tells us is that high mass stars form quickly, but they also die quickly. High mass stars do everything fast. Alright, so we have our high mass star on the main sequence. All main sequence stars, high mass or low mass, when they are on the main sequence, are in the process of hydrogen fusion in their core. However, the type of hydrogen fusion in the core of a high mass star is different than that for a low mass star. Low mass stars, like our Sun, go through the proton-proton chain, which we've talked about previously. A high mass star goes through what is known as the CNO cycle. So what happens is we start out with a carbon-12 nucleus. Onto that carbon-12 we then fuse a hydrogen, which gives off gamma rays, forming it into nitrogen-13. Nitrogen-13 is unstable, meaning it's going to spontaneously break apart and form into carbon-13. Onto this carbon-13 we then fuse another hydrogen, again releasing energy, forming nitrogen-14. Nitrogen-14 is normal, boring, everyday nitrogen. Onto this nitrogen we then fuse another hydrogen, which again releases energy, forming into oxygen-15. Oxygen-15 is unstable, so it breaks apart and turns into nitrogen-15. Then onto that nitrogen-15 we have another hydrogen come in, which then allows it to have a helium nucleus to break off, leading us back to carbon-12. Okay, so this is the CNO cycle because we go between carbon, nitrogen, and oxygen in this cycle. Carbon, nitrogen, oxygen, as we are slowly building up to helium. Now, you don't have to memorize all of the tiny little pieces in this whole thing. You need to remember that we're fusing 4 hydrogen together, creating a helium and giving off a lot of energy, except now we're using carbon as a backbone. We keep fusing stuff onto carbon until we pop off a helium. Now, after all of the core hydrogen has been used up, just like we saw before, we're going to, at first, have the core begin to shrink because it has less pressure. Now, as the core shrinks, it will leave behind a shell of hydrogen fusion, just like we saw in low mass stars. Now, at this point, we see the really big difference between high mass and low mass. We mentioned previously that for the low mass star, without that fusion, the core shrinks, but eventually it'll stop shrinking due to electron degeneracy pressure, because it's not going to get hot enough to begin helium fusion. And then it just sits there for a long time until other stuff falls onto the core, causing it to get hot enough that we get the helium flash. That's low mass stars. In a high mass star, as the core shrinks, it naturally heats up, and it will heat up to the point to begin helium fusion before it stops shrinking due to electron degeneracy pressure, meaning that the core shrinks, heats up, begins fusion, and then will expand back out. So, in other words, there is no helium flash in high mass stars. Helium flash is something that only happens in the low mass stars. So helium fusion is going to last for a few 100,000 years, converting helium into carbon as we saw before in low mass. Now, once the helium is all used up, the core is again going to shrink, and that will then trigger a shell of helium fusion, and we'll have that shell of hydrogen fusion. Okay, so the carbon core is going to continue to shrink. Now, every time that fusion ends in the core is going to shrink, which causes the rest of the star to expand. And so we see that on the HR diagram as the star swings off towards the right. Then, once it begins a new stage of fusion, the core is going to expand, which means the rest of the star is going to shrink and heat up. So we see the star swing back to the left on the HR diagram. And so on the main sequence, we have hydrogen fusion. Once the hydrogen is used up, the core shrinks, the star expands, and swings off to the right. Then the core gets hot enough to begin helium fusion. So the core expands, and the rest of the star shrinks, and it swings over to the left. Then it uses up all of the helium in the core, turning it into carbon. So fusion ends in the core, and the core shrinks, the rest of the star expands, and swings off to the right. So we have these stars that cycle back and forth as they're beginning and ending these different stages of fusion. Now, because of the high gravity that is crushing down on the core, it's able to keep getting hotter and hotter and hotter. So once the core temperature gets up to 600 million Kelvin, that is now hot enough to begin carbon fusion, which is then going to lead to heavier elements. Now remember, in a low mass star, once the core gets to carbon, that's it, fusion ends. It doesn't have enough mass to get to the temperatures and pressures necessary to begin carbon fusion. But in our high mass stars, we're able to fuse carbon, which is going to produce oxygen, neon, sodium, and magnesium. Now, in stars that are above 8 solar masses, these stars are going to have enough gravity to get to a high enough pressure and temperature that they'll be able to fuse even beyond carbon. So once the carbon is used up, these stars will begin fusing oxygen. After the oxygen is used up, the stars will begin fusing neon. When the neon is fused up, they'll begin fusing magnesium, and in each step, the core is going to shrink and heat. And then the magnesium fusion is going to, after that ends, we'll have silicon fusion, and the product of silicon fusion is iron. So at every stage, we're going to have more and more fusion, many, many different layers. So towards the very end of its life, we're going to have many different shells. So the core is going to be non-fusing iron. We'll talk about exactly why that is in a bit. Surrounding that non-fusing core, we have a shell of silicon fusion, then a shell of magnesium fusion, then a shell of neon fusion, a shell of oxygen fusion, a shell of carbon fusion, a shell of helium fusion, and a shell of hydrogen fusion. So we have all of these many different layers, each fusing different elements. This is going to provide a high pressure to the rest of the star, allowing it to expand a lot. These are what we refer to as supergiants, because they are thousands of times larger than our sun. So a red giant is around 100 or so times larger than the sun. Supergiants are thousands of times larger than our sun. These are the stars that if we were to replace our sun with one of these, it wouldn't just go beyond the orbit of the Earth. It would go all the way out beyond the orbit of Jupiter. These things are really big. Now, because at every stage we're going to have a higher pressure and a higher temperature in a core, that means that the fusion rate is going to be faster and faster and faster. So at every stage, we're going to have a shorter amount of time for that particular type of fusion. So, for example, we're looking at a 25 solar mass star. So what spectral type is it going to be and what color? So this is going to be an O-type star on the main sequence. It'll be an O-type star, and it will be blue in color. Alright, so it will go through hydrogen fusion for around 7 million years. Okay, notice I said million with an M and not billion. Okay, 7 million years. After the hydrogen fusion, helium fusion takes over, which will last for around 700,000 years. After helium fusion is done, carbon fusion begins, which lasts for 600 years. Not 600,000, just 600. After carbon fusion, neon fusion takes over, which will last for 1 year. After neon, we have oxygen fusion, which lasts for 6 months. And then last, we have silicon fusion, which will last for 1 day. Okay, think of how long a day is as compared to the lifespan of an entire star. Okay, these get really, really short.